So the ability to bear an impact load. Okay. So what is an impact? Where impact is when the force is, so it's usually a large force is applied for a very short duration. Okay. So what does it really mean to have very short duration? Like how do you quantify it? So the short duration really is to do with the natural frequency of the system. The short really here implies is it's less than 1/3 of the natural frequency of the system. So structurally, a material always has a natural frequency. This is the frequency at which something gets deformed. So if it's fast enough, that's 1/3 the natural frequency, then you can consider that to be an impact load. And there are many ways to figure out the impact strength, like the hardness, right? So two of the common ones, and which we'll talk briefly here, is the Sharpie notched bar test, and the second one is the ISOD notched bar test. Yeah, they have very similar principles, just differ a little bit in the way in which the specimen is loaded and how the test works. Test is kind of the same way, but just the specimen dimensions and things like that. So what exactly is the test? It's the same for both of them. It's a pendulum test. What you do is you take your specimen, you put it in a vise so it doesn't move. Specimen. So the vise is actually in the plane, which is in the plane of the paper. So I can't really draw it in a two-dimensional image. Then what you do is take a pendulum. On the pendulum, fix a notched bar. Release that notched bar from a certain height, h. It's called h1. And then when maybe I just misdrew this, I'm going to move it a little up. Okay, so now it's going to hit the specimen. So it hits the specimen, okay? And I'll show what the specimen looks like. It's basically a specimen is held in a vise. So that's the pendulum is coming in that plane. So it's really hard for me to draw it in that figure. And then once it hits, it basically breaks the specimen in two pieces, and then rebounds to a height h2. So what's happening here is bar hits specimen, breaks it into two, rebounds to a height h2. Now, if it was a perfect pendulum, then h1 would be equal to h2. But since the specimen is bearing some of the energy which the pendulum imparted, h2 will typically be less than h1. And the difference in the heights is because some of the energy is spent breaking the specimen into two. So in this case, so h1 is the start height. h2 is the rebound height after breaking the specimen. And that's where the pendulum or the notched bar is at rest, right? It swings to height h2. So then the energy absorbed by the specimen is simply the mass of the notched bar times gravity times the difference in the height. So it's going to be h1 minus h2. Yeah, I'm fixing that. Sorry about that. Yeah, thanks for catching that. Okay, so it's very simple concept, right? The change in energy, change in height of the bar correlates with the energy change, which is imparted to the material which is clamped. So as I said, what's how exactly the specimen is, maybe I should put a figure there. Let me finish this. Let me just keep this for a bit, in case you're writing this. Because as I said, the ISO and the Sharpie are different in the way the specimen is held, and I'll draw a figure which will illustrate what the difference is. It's a very minor difference. So this is what is done, how the specimen looks in case of the ISO test. So let's have the specimen vertical, and then that specimen is held in place by a vise. It's IZOD, Z ISO test. So this is our vise or the support system which keeps the specimen in place. This is our specimen. Okay, so the notch is, in this case, it's a notch here. The notch is basically helping the vise to keep the specimen in place. And then the final piece is the pendulum, which is swinging something like this. So it's going to go and impact and break the specimen into two. The Sharpie test, on the other hand, the specimen is put horizontally, something like this. PY, yeah. That's right. Like sharp. CHARPY. So same thing, this is put under a vice. And the pendulum comes swinging on the other side. So that basically breaks the notch. Okay, just very minor difference in terms of how it's done. So here the difference is A, the specimen is vertical. You can see that the specimen is horizontal. So there is two notches as shown. I couldn't show the second one. It's on the other side. Notch should be on the other side. It's hard to show in a 2D plot. And then this one would have either a V or a U notch. So I showed a V notch. Okay, so clearly if you do an ISO test, you probably will get different results from the Sharpie test because the way they've been set up. Yeah. It's I'm just showing you for information. So probably we won't test you on this kind of information because we don't really have sort of multiple choice questions. But and I know some of you will do this. You'll sign up for being a professional engineer, and if you see the professional engineering and there's a FE exam and so on, they are basically multiple choice questions. So that's where you probably want to know these things, small things, but they're important. Okay. So that's pretty much completes chapter 2. Okay, moving on to chapter 3 on stress is strain. That's like the central piece of this course. And whatever we run in stress strain, the next chapter is going to be very useful when we design elements, because when we are designing in this course, we're designing for worst case stress. So you want to know what the stress a material is going to have when you load it in tension, compression, shear, or whatever that is. Okay. So some of the things I'll start off are basic things we probably have covered in strength of materials, but it will slowly get new things which you probably have never seen before. So let's get started with chapter 3. We'll start with the basics, equilibrium, and FreeBody diagrams. Okay, so these are rules which you probably have seen in statics. You probably have seen them in dynamics. The same rules apply here. So first of all, you always want to draw a free body diagram. Okay, this point is minor, but I still like to include it, which is you want to then assign coordinate system. Sometimes that's part of the free body diagram, because when you say the net force in the x direction and you don't show the x direction, it just makes difficult for someone to understand what they're doing. So after you draw a free body diagram, assign the coordinate system. The third step is the basic equations which are used to analyze a system in static equilibrium. So if the body or the system, body or system, whatever you have there, is moving at constant speed, and or zero acceleration. Okay, as long as it's not accelerating, you can use the following equations. The sum of the forces is zero. The sum of the moments is zero. So that's like usually 3 equations in 3D. And the 3 equations in 3D for the moments, there are 6 equations. And so you can use those equations to solve for unknowns. Use these to solve for unknowns. And what are the unknowns? Well, they usually reaction forces or moments. Now, in this course, however, we will not be doing 3-dimensional systems, okay? We're just going to limit it to 2D systems. If you want to do 3D systems, there are advanced courses, typically at the 400, 500 level. You can take an elective course, which will teach you how to do this in 3 dimensions. So in 2D, which is the world of planar systems, we only have 3 as opposed to 6 equations. They are the force in the x direction is 0, assuming that the x and y is the system is in the plane xy. The summation of the forces in the y direction is 0, and the moment about any point is equal to 0. Okay, when you compute this moment, that moment is typically about the z-axis. So this is moment about z-axis, and I've shown the z-axis sticking out of the plane of the paper. So either you have clockwise moments or counterclockwise moments or clockwise moments, and those are those are considered to be in the z-axis. So you will not have moments in the x and y-axis because those are out of plane. So those are the equations we'll be using. So a common mistake people make when we do dynamics or statics is that they use that third equation more than once. So 2 times, 3 times, that doesn't, there are some certain things. So thinking, you can use that equation. However, you need to be careful about using that equation in the sense that that equation is not a unique equation. It's not that if you write that equation 3 times, that you will have a different equation. It's the same equation. So you always want to use those force in x, force in y, and moment at any point equal to 0. Don't keep using that moment at any point multiple times because it just is the same equation. And that's one way people get answers wrong. Though you can use it in smart ways to find forces without writing too many equations. And as you get more and more expert at this, you can figure out how to do that. But I recommend people to just write all those 3 equations and use those 3 equations. Okay, so then when we talk about free body diagram, we have to think of reactions, or these are typically the unknowns in the problem. So a specimen is loaded, there's external force, there could be external moment. Those are the knowns. We know how much load is being applied on the beam, for example. What we do not know is how that system is transmitting these loads to the floor or to other elements. So what we do is we need to figure out the reactions from the free body diagram. So I will show you a few systems or few machine elements whose reaction force you ought to sort of know or remember, so that you can use that to find the unknowns. Okay, so here are the things which you'll commonly see in machine elements. You'll see rollers. Okay, the two ways in which rollers are put, they are either shown using a circle, and then let's say there's a beam on top of it. So if you see a roller, then the free body diagram is going to be like this. Okay. What it means is if something is rolling, it can only transmit forces in the horizontal direction. It cannot transmit forces in the lateral direction because it's free to move in that direction. So example is this, right? The wheel there is you can move this in the forward back direction because it's not resisting anything in that direction. So the force in the horizontal direction is zero, but it is resisting motion in the y direction. So that's why you put R, and that's not equal to zero. The other one, which is we'll probably not see too much in this course, is the cable, but I'll put it anyway. So a cable is something which is a string-like element. So a string, as you know, can only bear tension. It cannot bear compression. And so what you'll do is when you draw the free body diagram, you'll only show tension. And it will always be along the string, right? It cannot bear a force in a direction which is not along its length. The more common one is a pin joint or a hinge joint. The way we'll denote this joint is something like this. Okay, and so let's say there's a beam which I'm going to cut, and when I draw the free body diagram for the pin joint, I need to replace it with two forces. One would be in the vertical direction. So if you like, call it Fy, Fx. Some people like to call this, I like to call this V, denoting the vertical force, and then H. So if this point is, let's call this point A, then I typically like to call this as VA, HA, just to denote that it's the force at A, and there is H for horizontal, V for vertical. Some other people would like to call it, some people like to do it like this way, AY. That shows that the force at A, and Y denotes the direction, AX. So if the force at B, it will be BX, BY. So I really have, it's very flexible. You can use whatever notation you like. Okay? You don't have to stick to my notation or the one in the book, as long as it's meaningful. Like try to put names which make more sense. For example, if your X direction is to the right and Y direction is up, don't use Fx in the vertical direction, because when you solve the problem, you yourself will be confused. Just use something which is consistent and which is meaningful and easy to remember. The other way you can show this force is you can show it by a force F, magnitude, and an angle. So F at A, which is fine because that FA can be resolved into two forces. One is vertical and horizontal, and that's a perfectly fine way to represent the pin joint force. The last one is, and by the way, why is it that there are two forces and there's no moment, right? It's because a pin joint, it resists motion in the horizontal and vertical direction, just like this one resists force in the vertical direction, but it does not resist any rotation, right? That's why the force in, or the moment in the C plane is zero. And then the final one is fixed support. So that would be a cantilever beam. Typically, for example, used in a bridge. It's shown in this way. Okay, the way you show the forces here are, the free body diagram is, just cut it here. Will be Fy, Fx, and something more to it, because a cantilever beam resists rotation. So you cannot, the slope at this point, the attachment point is always zero when this starts bending. So it basically resists rotation, and so you need to put a moment in. And so those are the four common systems we'll see. In fact, we'll not see too much of cable, but the other three, 1, 3, and 4 are very common. Okay, so let's now try to solve a problem based on what we have so far. So example, here's a cantilever beam subject to well, it's loaded by a point force of 500 newtons, the length of 1 meter, and the total length of the beam is 6 meters. So typical question is, draw the free body diagram. B, compute reaction forces. Okay. And the other piece of information which I should have put here is that the mass of the beam is 100 kg. Okay, so let's just go through that whole process of computing things of interest, the reaction forces. First, draw a free body diagram. So we separate out the beam from the wall and replace the effect of the wall with forces. So there'll be a force in the y direction. Force X is to the right, Y is positive upwards. And since it resists rotation, we would have a moment in. Okay, so that's the reaction forces, but we also have to put all the external forces when we draw the free body diagram. So that's 500 newtons. And then we're going to make an assumption when it comes to the self-load, which is 100 kg. We're going to assume that it's equally distributed, and so that load will be applied at the center of the beam. So that's going to be here. So it's 100 times 9.81, which is mass times gravity, and that's at a distance of 3 meters, right? 3. This is 1. So this is a complete free body diagram because it has reaction forces and it has the external forces. And when you're drawing a free body diagram, it's considered free. So you're not supposed to show the wall, because then it's not free. It's fixed to the wall or to the ground. So we got that. Let's solve for the reaction forces. So here we invoke the 3 equations. First one, let's compute the force in the x direction. That should be equal to 0. And that trivially tells us that the force is trivial in the x direction, 0. Next, we have Fy equal to 0. And so we have Fy. And so let's stick to the sign convention that positive is upwards and negative is downwards. So Fy is assumed to be, we assumed it to be upwards. And you can assume it to be downwards too. That's not a problem. You'll actually see that when you compute it, it can come out with the right sign. And then there's 50, which is acting downwards. And then there is 100 times 9.81, which is 981, acting, so 98.1. Oh,
Professor?
sorry,
Professor?
yeah,
It's 500, not 50. It's 500 newtons, right?
good catch. Yeah, 500. That was somebody from Zoom. Equals 0. And so Fy equals 1481 newtons. And then the final part is the moment is 0. Okay, now that we have a couple of options, we can take moments about any point we choose to. And so this is where you typically want to choose a point where most of the reaction forces pass through, because those reaction forces will be eliminated when you take the moment. So if you choose, for example, this point, the place where the mass is, center of mass is, then you'll see that you still have to find the moments due to Fy. Fx probably passes through the center, so it's 0, and then Fy and 500. So you could do that, or often people like to put that point, choose that point to be the point at which the maximum forces, reaction forces are, because you may not know the right answer to those reaction forces, and by putting that point there, you're eliminating those forces. So let's choose it to be, let's say A. So moment about A is equal to 0. So we have M, and the way I've drawn the moment M here is clockwise, right? So I'm going to put a negative sign because the convention is counterclockwise is positive, plus 500, and the distance of that force from the point A is 1 meter, so it's force times distance, that's the moment arm, plus, okay, so again, sign convention. Since it's 500 and it's torquing the system clockwise about A, right, it's causing a moment this way, I need to actually put a negative sign. And same for this force. This force is also going to torque the system clockwise. So I need to put a negative sign both places. It's negative, and then negative 981 times the distance from the force to the point A, that's 3. So the moment is negative 3443 Newton meter. Okay, minus M is because clockwise is negative for our convention. Okay, you could totally start assuming it to be counterclockwise and you should be fine. So what happens here is that you see that you got a negative sign. The negative sign indicates that my assumed direction for the moment was incorrect. It is, thank you. It just says that this tells me that M is actually counterclockwise. So the nice thing about these formulas and the way this works is you really don't have to start assuming the right direction. The math will tell you what the right direction is. So the minus here indicates that this moment is actually in the other way, the way I assumed it.
Clockwise is negative, counterclockwise is positive.
Yes, that's what I did. So we have M, this is right. And then it comes out to be negative. So yeah, my bad. This should be Oh yeah, so yeah. Yes, this is actually, yeah, that was right. So what this is saying is that it's negative, but it's negative of this, which means it's actually, this force is actually this way, which is positive, I agree, but this sign is not indicative of this sign here. It's just telling you that the direction was opposite to what I started. So it's a bit confusing, but that's what you need to interpret it as. That this is, maybe a better way to say this is M is, this, the sign tells me that M is actually opposite of what I started with. Okay, nothing's about clockwise or counterclockwise. Okay, so that was a sort of a refresher, a relatively easy problem. But let's do a more involved one. Yeah. So two things going on. One is our convention, and one is the final answer, right? The convention I used throughout this problem is clockwise is negative, counterclockwise positive, and that's why this sign is negative. When I solved the problem, it came out with a negative sign. So this negative sign here is just saying that the M in this figure is opposite of what it should be. Right? The opposite of this is that way, right? This is the actual. And so that actual is counterclockwise, and counterclockwise is positive. So the other way to solve this is to start off with that direction, the actual direction, and you see answer is going to be positive, which is saying that you started off with the right direction for M. Okay, so I'll do another problem. So hopefully it'll get clear. But yeah, moments can be confusing because of this intricacy. Okay, so here is a slightly more advanced problem with more forces. Okay, the question is find the reaction forces in the beam I'm going to draw. So reaction forces at A and B. So here is the beam. So roller support on one side, twin joint on the other. And this is A, this is B. And now let's see the forces. So there is a 200 Newton force at B. There is a 100 Newton force somewhere in between. And that is about, well, it's 2 meters to the right of B. And then there is an oblique force over here. So this way. So that's is 600 newtons. It's at 45 degrees. Okay, and then this is needed here. That is, this is the center line. Okay, slight change in the way I drew this. This pin joint is right here in the middle, and then this force is on the surface. And so the distance between the surface and the midline is 0.2. Okay, so remember that this pin joint is at the middle. Okay, so there are three forces. So let's start with the free body diagram. Okay, now we got to go back and review what reaction forces occur due to roller and pin joint. For the roller, there's going to be a force in the vertical direction. And I'm going to use a slightly different notation here. I'm going to use my notation that V is vertical to show X and Y. So the force in the vertical direction at A is VA, and that's the only force. For B, there would be a force in the vertical direction, and that's going to be VB. And now I can, so again, when I assume the force direction, you can assume it to be anything. I'm just going to assume that the horizontal force is H, and that is to the left side. And as I said, you could assume it to be the right side too. It won't really affect anything. Then this force is 100. This force is 200, like newtons. And then I could keep that force, which is 600 newtons at 45 degrees. But what I think is it might make it much easier if I actually resolve it into two components, one in the vertical and the other in the horizontal direction. So what I need to do is I need to take 600 cosine 45, and then I get 424. So what is 424? It's 600 cosine 45 degrees. And then if I resolve it in the vertical direction, it's going to be 424 again, but this time 600 sine of 45 degrees. Okay, so that free body diagram now has all the forces, and I'm all set to find the reaction forces. Okay, let's start with the easiest one. The net force in the x direction is equal to 0. So here we have 424. Okay, so you can see 424 is pointing to the positive x direction. So we can just say that's our convention. So we stick a positive sign there. And then HB, which is the only force in the horizontal direction, is towards the left side, which is around the negative x. So let's put a negative sign to it. This gives me HB equals 424. Okay, the next equation I'll write is the net force in the y direction is 0. So again, our convention is going to be positive is upwards, negative is downwards. So VA is positive, it's upward. VB is positive, it's upward. 100 newtons is downwards, it's negative. 200 is downwards, negative. And then 424 is downwards. So if you sum that up and move things around, you get VA plus VB equals 724. Okay, so this equation here, unfortunately, doesn't let us solve for VA and VB. It only gives a linear combination of the two. So we need to invoke the third equation to solve for VA and VB. So what we'll do is we'll take moments. Now, you have multiple choices to take moments. You could take moments about A, you could take moments about B, you could take moment at 100 newtons or to that 600 Newton force, wherever you choose to. The recommendation is usually if you take it at one of those reaction forces, then it will eliminate those forces in that equation. So let's say that that point is B, right? If you take at B, HB and VB will effectively be eliminated. And that's why you want to take it at some of those places. So just to show you, I'm just going to take it at A, but you could do it at other places. So moment at point A is equal to 0. So that, as I said, effectively eliminate VA. So let's just write that down now. So we're going to use the convention. Clockwise is positive and counterclockwise is negative. This is our point. Okay, so let's start. So we have 424. This one. It's acting in the, so about A. If you can imagine that force, if that was the only force and the beam was free, it will move the beam in the clockwise direction. So that force is clockwise about the point A, and the distance, the moment arm is 0.2, which is actually shown over here. So we need to put a negative sign. Next, the force 424, which is acting vertically downwards. That force is inducing a clockwise moment about A. So again, negative sign. And the distance is, I believe it's 2 meters. Next, we have the 100 Newton force. So about A, 100 Newton also induces a clockwise moment, so negative sign. The distance from the 100 Newton force and A is, if you look here, it's 3 plus 2, so it's 5. And then we have HB, which conveniently passes through A. So the moment arm due to force HB is going to be 0, right? Because it passes through the center. That drops off. So we're only left with VB and 200. So 200 is clockwise about the full length of the beam. So it's 3 plus 2 plus 2, that's 7. Minus 200 times 7, then minus for the clockwise movement. VB is going to produce a counterclockwise force or counterclockwise moment about A. So VB will have a positive sign for the moment. And then the distance is, I think it's the same as that, 7. So now we have an equation for VB. Solving for VB gives us 405 newtons. What we can do is now putting VB equals 405 in 1 gives, okay, VA, which is 319 newtons. So that's it. So this is how we solve for VA, but the other way to solve for VA is you could do moment about B equal to 0, and then this will also give you VA equals 319. This is the alternate way to do this. In this case, you will not require this equation to solve for VA. You can only use the moment equation. So this is a case where I use the moment equation twice and solve for VA and VB without using F5 equals 0. Okay, so